Thank you for the introduction. This talk is about utilizing the convolutional neural network to classify the EEG-derived motion components in the simultaneous acquisitions of EEG and fMRI. As you will see, the developed method allows possible real-time application of the head motion correction in fMRI on a slice-by-slice basis. When subject moves inside the scanner, there is change of magnetic flux within conducting path on the scalp. Faraday's law tells us that whenever there is change of magnetic flux, there is induced EMF or induced voltage. EEG records the motion-induced voltage with a high temporal resolution. We call that EEG motion sensor. As the subject head motions inside the scanner is small, the time integral of the induced EMF is approximately linear to the head rotation angle. The head rotation angles, and hence the EEG motion sensor can be utilized for retrospective slide-by-slide motion correction in fMRI. Here shows the previous results using the EEG motion sensor. The upper left figure shows the improvement in the temporal signal-to-noise ratio on the axial ring slices after the slide-by-slide motion correction using the EEG motion sensor. The lower left figure shows the stripes in the correlation map caused by the subject motion, the corrected correlation map after the motion correction using the EEG motion sensor, and the difference. The lower right figure shows the reduced stripes in the group correlation map after the motion correction for groups with severe motions during the scan. The motion-induced EMF or the EEG motion components can be extracted from the independent component analysis and automatically identified by rule-based algorithm. For the independent components or ICs related to the spontaneous head motions or motions induced by cardiac pulsations, that is the cardioballistic motions. There are spikes in the time courses of the ICs. In the power spectral density of ICs related to motions, there are either convexity features in the frequency range from 0.5 to 4.5 Hz or peaks in the frequency range from 2 to 7 Hz. Also, the spatial projection topographic map exhibits either symmetric or asymmetric opposite polarities. Finally, when the IC is removed from the EEG signal, the spike in the EEG time course reduces significantly. The rule-based algorithm analyzes the IC time courses, power spectrum, topographic map, and the reduction of spike in the EEG time series by comparing these properties with threshold parameters. Depending on the motion severity of the subjects, the rule-based algorithm takes about a minute or two to identify the motion ICs for each scan. On the other hand, a pre-trained motion IC classification model using the machine learning approach calculates the probability of being a motion IC by matrix operations. These calculations can be much faster, especially with the use of GPU. Therefore, a pre-trained motion IC classification model is more desirable as it allows real-time possibility of EEG motion sensor. Also, it benefits from a large IC dataset and allows convenient models update. The motion IC classification is evaluated by convolutional neural network, or ConvNet, carried out with Theano in Python. This shows the ConvNet we used. It includes 2 convolution layers, followed by 1 or 2 hidden layers, then a logistic regression layer, and the output layer. We chose the ConvNet because of the convolution layers that improve the feature recognition efficiency by filtering the local patterns of the input features regardless of the positions. On the experiment side, there were 1,040 scans from 56 subjects. Each scan lasted for 526 seconds, with the first second removed to ensure the steady-state signal. We preprocessed the EEG signal by removing the MRI artifacts and then performed the ICA to separate 31 ICs in each scan. There were a total of 32,000 ICs. among which 3,800 are motion-related. For each IC, we obtained the spatial projection components, power spectrum, and the statistical properties of the IC, such as the maximum, minimum, standard deviation, kurtosis, skewness, energy, etc. We noticed that simultaneous changes of the size of the spatial projection components and the IC time courses give identical EEG signal. Therefore, we doubled the data size by simultaneously flipping the size of the spatial projection component map and the IC, giving a total of 64,000 datasets. 38,000 were used for training, 12,000 for cross-validation, and 12,000 for testing. We used the cross-validation data to optimize the model parameters, leaving the test data untouched during the training stages. For comparisons, we used the multi-layer perceptron neural network and support vector machine model. For MLP and SVM, 92 classification features were used. They are the 31 spatial projection components, 50 data points from the power spectrum below 12 Hz, and the 11 IC statistical properties. For the COVNet, 831 classification features were used. The difference is that instead of using the 31 spatial projection components, we used 768 points from the interpolated spatial projection map. The classification efficiency is evaluated on the test data set based on the accuracy, precision, recall, and the F1 score. We compared the results with different data sizes, separated or combined label for the rapid, spontaneous head motion and cardiobalistic head motions, 1 or 2 hidden layers following the convolutional layers, and 1 or 2 hidden layer MLP and SVM. Classification accuracy for all models reached over 97% on the test data set. The COVNet achieves highest accuracies compared to the MLP and SVM. Also, the COVNet with the combined classification label for spontaneous head motions and cardiobalistic motions gives higher accuracy. Also, we noticed that although the test accuracy and the F-score are similar for different models, the precision and the recall are more balanced in the model trained with doubled data size, interpolated spatial projection map, and both combined classification labels for the spontaneous head motion and cardiobalistic head motions. However, the improvement is little and seems bounded. Therefore, we want to examine the classification results and check what led to the false classification. Here shows some examples of the true positive, true negative, false positive, and false negative classifications of the motion ICs. Examples, the ICs in the true positive classification examples are the textbook standard examples for motion ICs, showing opposite polarity in the topographic map, peaks in the motion frequency range of the power spectrum, and significant spike reduction in the EEG time course when the IC is removed. The ICs in the false positive classification examples are regarded as non-motion ICs because there is no significant spike reduction in the EEG time series, even though this IC shows textbook standard topographic map and power spectrum for motion ICs. The ICs of the false negative classification examples are motion ICs because the topographic map, power spectrum, and the signal spike reduction in the EEG time course satisfy the condition for a motion IC, even though this IC does not have textbook standard topographic maps. From the examples of the false positive and false negative classification, whether the IC is motion related or not is critically dependent on the EEG signal contribution of the IC. That is the spike reduction in the EEG time course when the IC is removed from the EEG signal. This suggests that we need to also include the EEG signal contribution of the IC in the classification features. Finally, it takes about 1.6 seconds to classify 12,000 ICs in the test data set. In conclusions, accurate and fast motion classification is achieved based on the IC spatial projection components, power spectrum, and statistical properties using the convolutional neural network. Signal contribution of the IC should be considered in the input features in order to further improve the classification accuracy. Accurate and fast classification of the motion ICs allow the real-time application of the EEG motion sensor for the motion correction in fMRI on a slice-by-slice basis. Thank you.
Do we have any questions? I actually had a couple. So all of the methods that you compared, they actually have quite high level of accuracy, something like 97%. Do you, so this is relative to then a human rater identifying what is artifact and what is not, is that right? Mm-hmm. So how accurate are people in doing this? I mean, is it possible that you're hitting a ceiling with respect to whether people are, that quite possibly what you're running into is misclassification with respect to the ground truth, or?
It could happen that there's human error in the classification, yeah. But as I show you in the result, it could also happen that we need more features in telling the information about the ICs.
Right, yeah. I guess another thing is that, so I'm familiar with this sort of thing in the context of fMRI. And one of the things that you find when you're cleaning up fMRI data is that a classifier that you train that works on one data set is not necessarily totally generalizable to data that's acquired with a different protocol or in different populations. How do you expect that to behave in EEG? Is it likely that if I have, for example, data I've trained on a large number of channels, is that going to be, can I just use that classifier on data that has different properties, or?
Different properties such as?
I don't know EEG, so I can't really, I mean, all I can think of is like something like the number of channels, or, you know, or something about the environment that might make you more or less sensitive to certain types of errors.
Okay, if you use more number of channels, I would expect there's improvement in the classification accuracy because there are more features, but we don't know until we try it.
And is the work that you've done so far, that's all, the data, is the data all very, very similar from like the same EEG system then, or have you got lots of data from different types of systems included in this?
From the same system.
Okay, great.
Thank you.
Yes, there's one question here.
Yeah, it occurs to me that there's another feature of the EEG that might help you in this, which is the fact that the EEG leads themselves. They wiggle, they have their own oscillatory modes to them. And it might be that you can identify specifically motion-related effects in the EEG by the extent to which the time course of those EEG motions look like a convolution of a motion on the modes of the EEG wiggling, right? So that's as distinct from other sources of artifact that could have nothing to do with the translation of the leads.
Okay, so thank you. Okay. Thank you.
If this one's really quick.
Yeah, well, so my question is, why go to all this trouble when we have lasers that can identify the motion of the head and correct the gradients as we go?
Can you say that again? Sorry.
So what is the advantage of using such a correction system that requires to put leads on and to record EEG at the same time that you're recording fMRI, which is not a simple procedure, when we have motion detectors from outside that can modify the gradients as we go?
This is another way of measuring the motion. It comes with the multimodal imaging of the EEG-fMRI. So that, yeah.